Welcome to Miss Smith's Math Tutorials. I'm Miss Smith. In this video, we're going to be talking about rational function characteristics. By the end, you're going to be able to look at a rational function equation, and you're going to be able to say, are there any holes? What is the x and y intercept? Are there any vertical or horizontal asymptotes? And also be able to state what is the domain and range of that rational function. I've graphed over here just for you to look at a basic example of a rational function. So we've got our x-axis and y-axis, and then if you'll notice these blue lines right here and right here, that would be our rational function. The green lines, the green dashed lines, and also our little markings here, we're going to get to those and what those are, but really what I want you to focus on is just the blue shape there. That is a basic rational function. The first step when we are given a rational function equation is we want to factor the numerator and denominator if possible. And sometimes we'll be able to and sometimes we won't. But if we can, we definitely want to do that. You want to get it into its most simplified factored form. Our next step would be to write the simplified version by canceling any common factors in the numerator and denominator. So in order to determine if your rational function has a hole, we would first want to find the x value. And a hole would look like this right here. So notice in our blue line right here, there's just kind of an open circle place right there. That would be an example of a hole. Now, if you were to graph this on your graphing calculator, it's not going to show you an open circle. It's just you're going to have to zoom in super close, and it's just going to show you like just a minuscule little gap in that area. But when we see it drawn, typically we'll show that with an open circle, that there's a hole in that graph. So in order to find the x value of a hole, we set factors that occur in both the numerator and denominator equal to 0, and then we solve. So what that's saying is when we do this step right here, this simplified version, where we cancel any common factors, what we're saying is we're going to take those common factors, if we have any, we're going to set them equal to 0, and we're going to solve. And then we would write that one part as x equals and then whatever the value is. That's going to tell you your x value of the hole right there. To then find the y value, we take the simplified version. So we've canceled out any common factors. We take the simplified version and we replace all the x's with the x value of the hole. So whatever we get right here. We'll replace all the x's with whatever we get right here. And then we'll simplify. And we'll write that part as y equals whatever we get. And then our final answer for that would be written as there is a hole at the point x, comma, y, whatever our two values here are. And that will tell you the coordinates of where the hole actually is. Sometimes you won't have a hole, and that's okay. This is just a way to tell if you do. To find an x-intercept, you want to set the remaining factors in the numerator equal to 0 and solve to find the x value of the x-intercept. So what that means is, once we've already found our simplified version, whatever is left in the numerator, so we've already canceled out any common factors, and whatever we have left in the numerator, we're going to set it equal to 0. And we're just going to solve it. And that's your x-intercept. So some teachers prefer you to write that as x equals whatever the x-intercept is. Other teachers, and my preferred method is just to write the point of the x-intercept. So it falls at whatever the number is, comma 0, because that'll tell you the exact point on the graph. And here's the example of the x-intercept. So we're basically just looking at where does the blue line cross the x-axis. That would be your x-intercept. To find your y-intercept, you want to plug in 0 for all the x's and simplify to find the y value of the y-intercept. So again, this is after we've canceled any common factors. Whatever we have left in our simplified version, we just plug in 0 for all the x's and we simplify it. That's going to tell you where your y-intercept is. And you could write that as y equals whatever the number is. Or you could write it as a point, as a coordinate point on the graph, that the y-intercept falls at 0, comma, whatever, right? And here's the y-intercept right here. We're looking at where does the blue line cross the y-axis. A vertical asymptote, I've labeled it VA, and it's this green dashed vertical line right here. That is our vertical asymptote. And in order to figure out where that green line falls, we would set the remaining factors in the denominator equal to 0 and then solve. So whatever's left in the denominator after we cancel out any common factors, we would just set it equal to 0 and solve. And then we would write it as x equals whatever we get. So it means that that blue line approaches the green but doesn't cross it. And this blue line approaches that green and it also doesn't cross it. So that's called a vertical asymptote. To find a horizontal asymptote, so that's our HA right here, and it's this green dashed line that we've created right here, this horizontal line. So to find the horizontal asymptote, we compare the degree of the numerator to the degree of the denominator. So you ask yourself, what's the highest exponent in the numerator? What's the highest exponent in the denominator? And then that will tell you what your horizontal asymptote is. Now there's 3 different scenarios, and we've got this acronym here to help us remember the different scenarios. So we read this as BOBO, BOTN, EATSDC. So BOBO would stand for bigger on bottom. So if the exponent, the larger exponent is in the denominator, then your horizontal asymptote falls at y equals 0. So that BOBO, that last O, is really representative of a 0. So bigger on bottom, y equals 0 is your horizontal asymptote. Next we have BOTN, which stands for bigger on top. If your highest exponent is in the numerator, that means there is no horizontal asymptote. And then the third option is EATSDC. So that would be if when you compare the highest exponent in the numerator and the highest exponent in the denominator, and the exponents are the same. So that's our EATS, exponents are the same. Then what we do is DC. We divide the coefficients. So whatever is the number out front of the letter in the numerator and the number out front of your variable or letter in the denominator, you just divide them. And if it reduces, great. And if it doesn't, then it's just a fraction. And when we get that number, we would always write it as y equals whatever the number is, because we're creating a horizontal line right there for our horizontal asymptote. When we go to find the domain of a rational function, it's pretty easy, but there's different ways to write it. Essentially though, it's just gonna always be all real numbers, okay, which we also, another way to say that is negative infinity to positive infinity, all real numbers. But x cannot equal, okay, that's what that little equal sign with the slash through it, it's saying that x cannot equal the vertical asymptote, so whatever number we get right here, or the x value of any wholes. Okay, so looking back up here, when we find the x value of the whole, whatever we get, that cannot be part of the domain. So remember, when we look for domain just means our x values. So we're saying that when we find the domain from left to right, okay, our left would be negative infinity, because we've got this arrow stretching on for negative infinity. Our right would be positive infinity, because that arrow is going to keep going on forever. But we have to take into account the gaps, right? So even though I hit an arrow there, which would mean negative infinity, I've got to be careful, because as I keep moving, look, there's this hole right there. And we've got to take that into account. And then if I keep moving even further, there's another gap here for this vertical asymptote. So there's a gap there and there that I need to account for. So that's why we say it's all real numbers, but x cannot be the whole, the x value of the whole, and it cannot be the vertical asymptote. Similarly, with range, it's also going to be all real numbers, but we've got a caveat here that y cannot be the horizontal asymptote, or the y value of any wholes. So again, similarly, when I go to find my range, when I pull up from the bottom, I see an arrow, which would mean negative infinity. And when I pull down from the top, I see an arrow, which would mean positive infinity. But we've got some gaps here, because if I were to keep going, look, there's that hole right there. And then right directly above it, there's also that green horizontal asymptote. So we've got to take into account those two gaps when we're finding the range. So when we get into some examples where we're going to write out our domain and range, I'm going to show you both a formal and an informal way to write it. Let's look at some examples together. So we've got f of x equals, and remember f of x is just another way to say y. So we've got y equals x minus 2 times x plus 4 divided by x minus 2 times x minus 1. So a common student error is they want to FOIL these because they say, oh, that's a binomial times a binomial. That means I'm supposed to FOIL and go ahead and distribute. We don't want to do that. This is actually already perfectly factored exactly as we want it. If I were to FOIL either the top or the bottom, you're going to end up with a quadratic in standard form, which doesn't help us. So when you see parentheses, that's awesome. We don't need to do anything else to it other than moving on to that next step, which is to simplify by canceling any common factors in the numerator and the denominator. So looking at this, you ask yourself, do we have anything that shows up in the numerator and in the denominator? And hopefully you're seeing this x minus 2, right? And it doesn't matter that they're right on top of each other. I could have the x minus 2 over here. Order doesn't matter. It just matters that they're the same. So I can actually go ahead and cancel those out. And then when I simplify, I want to just rewrite the same problem, but with the canceled out versions canceled out. So in my numerator, I would have x plus 4. And in my denominator, I would just have x minus 1. So on the first page, we talked about how to find a hole in our equation if there is one. We always want to find the x value first. So to find the x value, we set the factors that occur in both the numerator and the denominator equal to 0, and then we solve. So that goes back up here to where we said, okay, we canceled out these x minus 2's. We canceled them. So whatever you cancel, we want to rewrite that. So in this case, it's just x minus 2. Right? We don't need to write it twice. That's the one canceled factor, so we just write it once. We set it equal to 0, and then we just solve for x. So looking at this is just a one-step equation, right? X minus 2 equals 0. All I would need to do is add 2 to both sides. And now we just have our x equals 0 plus 2 is 2. So now we know the x value of our hole. It's just 2. Now to find the y value of the hole, remember that we take the simplified version of the equation, which we have right here, and we replace all the x's with the x value of the hole, and then we simplify. Okay, so we're just going to rewrite this, but we're just going to replace all the x's with 2's. So this would be a 2 plus 4 over a 2 minus 1. Now 2 plus 4, that would give us 6. And 2 minus 1, that would give us a 1. Now 6 divided by 1 could just be written as 6. And that's our y value of the hole, our y coordinate. Y equals 6. So what this tells us is we have a hole at the coordinate point 2, 6. Next we can find the x-intercept. So remember that we can find the x-intercept by setting the remaining factors in the numerator equal to 0 and solve to find the x value of the x-intercept. So once we simplify, we've canceled out and we've got this simplified version. We just take the remaining factors in our numerator. Remember, numerator just means the top. So in this case, it's just x plus 4. So all you have to do is do x plus 4 equals 0. And then we would solve that for x. So we would want to subtract 4 from both sides. And over on this side, we just have x. I'm going to scooch it over here just for space. And 0 minus 4 is a negative 4. So you could leave it like that to say your x-intercept falls at x equals negative 4, or I like to actually write it as a point, which would be negative 4, comma, 0. That's where your x-intercept is located. To find your y-intercept, remember that we plug in 0 for all x's and we simplify to find the y value of the y-intercept. So we go back up to our simplified version, and just instead of writing x, we're going to write 0. So for the top, we have 0 plus 4. And for the bottom, we have 0 minus 1. And we just want to reduce that. So 0 plus 4 is 4. And 0 minus 1 is a negative 1. And we can reduce that. 4 divided by negative 1 is just negative 4. And you could either write that as y equals negative 4, or my preferred way, you could write it as a coordinate point. So we know that the y-intercept falls at 0, comma, negative 4. To find our vertical asymptote, remember that we set remaining factors in the denominator equal to 0, and then we solve. And we'll write our answer as x equals whatever we get. So when we look at the simplified version, we just say, okay, what do we have left in the denominator? So in this case, we have x minus 1. So all you do is you put x minus 1, set it equal to 0, and then solve. So again, this is just a one-step equation. We just want to add 1 to both sides, and we end up with x equals positive 1, because 0 plus 1 is just 1. So that tells us we have a vertical asymptote at x equals 1. To find our horizontal asymptote, remember that we compare the degree of the numerator to the degree of the denominator. So we take our simplified version, x plus 4 over x minus 1, and we figure out what's my highest exponent on the top and what's my highest exponent on the bottom. You might be thinking, well, I don't see any exponents. But remember that if we have just a variable, so in this case just x with no exponent, it does have an exponent. The exponent is 1. So we would say the degree of the top is 1. And when we look at the denominator and we say, okay, what's our highest exponent? Well, we don't see one. So what has to be the exponent on the x? Was just a positive 1. So the denominator also has a degree of 1. So this is an EATSDC situation. So remember, EATSDC stands for exponents are the same, right? Because it's just 1 over 1. So exponents are the same. So what do? We divide the coefficients. So in this case, there's no coefficient that we see out front. You may be thinking, oh, is that the 4? No, that's a constant. A coefficient is what's in front of our variable. And in this case, it's just a positive understood 1. And the same thing on the bottom. There's no coefficient that I see, so it's just a positive 1. So when I divide my coefficients, I just say, okay, what's 1 divided by 1? Well, 1 divided by 1 is just 1, right? So we would say our horizontal asymptote falls at y equals 1. So remember, our domain is just going to be all real numbers, but there's something very specific we have to remember. We have to remember that we cannot include the x value of any wholes, and we cannot include the vertical asymptote, which I'm just going to shorthand as VA. So let's think about where we had wholes. So we just had one whole, and it occurred at 2, 6. The x value was 2. So we have a whole at x equals 2, and we have a vertical asymptote. Let's think back where that was. That was at x equals 1. The formal way to write it would be we go from negative infinity all the way up to the lowest gap number, meaning you look at the 1 and the 2. Well, which one's lower? The 1. So we start with that one. So it goes from negative infinity to a positive 1. And then it cuts off there, right? And we use this U, which in math means union, to show that we've got a gap right here from 1 to 1. And then we pick back up with the next highest number, so 2. So we've got another gap from 2, union 2. And then it just continues on from there to positive infinity. So that's the formal way to write it. The informal way to write it would be to just say that our domain is all real numbers. And that little symbol is just, I always think of it like an A and then an R cut through it for all real. So our answer is all real numbers, negative infinity to positive infinity, but x cannot be 1 or 2. So formal way to write it, informal, little bit easier way to write it. Now to find our range, remember it's also all real numbers, but y cannot be the y value of whatever holes we have, and it also cannot be the horizontal asymptote. So let's think about where the hole was. So we had a hole at y equals, and the y value of the hole was 6, right? We found that there. It is 6. And the horizontal asymptote was at, we found it was at y equals 1. So when we go to write our range, we can do it in a formal or an informal way. I'll start with the formal. So very similar pattern to here. We're just going to say negative infinity to the first gap, which would be between 1 and 6. Well, 1 is lower. So we say to 1, union 1 to the next gap, which is 6. And this is saying we have a gap at 6. And then from there, it continues on for infinity. Now the informal way to write our range would just be to say it's all real numbers, but y cannot equal 1 or 6. You'll notice I went back and boxed each of the answers. I realized looking back at it that it was a little hard to see what the actual answers were through all the work. I'll do that moving forward as I find the answer to each one. I'll make sure to box it. So in our next example, we've got y equals 5 divided by x minus 7 times x plus 2. So our first step is going to be to simplify. Can we factor anything? And looking at this, I don't have anything to factor. This the numerator is just a constant, and then the denominator is already in that nice parenthesis factored form. So there's nothing for me to do factor-wise. As far as canceling any common factors, do I have anything that occurs in both the top and the bottom like we did here? And looking at this, no, there's no common factors. So in this case, the original version is our simplified version. There's no change there. So when we look to see if there's a hole, remember we first always find the x value. So we set factors that occurred in both the numerator and the denominator equal to 0. So like here, we had those canceled factors, so we set that factor equal to 0. Here, notice there's nothing for us to cancel. So in this case, there is no hole. So we would just put none. To find the x-intercept, we set, once we get our simplified version, which we already had, we set the remaining factors in the numerator equal to 0, and then we solve. So my numerator is just 5, right? So, okay, we'll set 5 equal to 0, and then we'll solve. Now, hopefully you're looking at that thinking, that doesn't look right. There's nothing for me to solve for. There's no x, there's no variable, and ask yourself a question, does 5 equal 0? No, right? 5 does not equal 0. So all this tells you is that there's no x-intercept in this example. We would just put none. All that means is that this graph does not cross the x-axis at any point. To find our y-intercept, remember that we plug in 0 for all the x's and we just simplify. So I go to my simplified version and I'm going to rewrite it, but anywhere I see an x, I'm going to write a 0. And now I just want to simplify it. So 5 in the numerator, there's nothing I can do with that. So let's think, what's 0 minus 7? Well, that would just be a negative 7. And what's 0 plus 2? Well, that would just be a positive 2. Now this is a negative 7 times 2, which would give us 5 over negative 14. We would ask ourselves, does that reduce? And it doesn't. We could approximate it to a decimal. 5 over negative 14 is approximately negative 0.36. Either way is fine. It doesn't matter which one you use. So we know that our y-intercept falls at 0, comma, and I'll just use the fraction version, negative 5 over 14. To find our vertical asymptotes, we set the remaining factors in the denominator equal to 0, and we solve. So in this case, I actually have 2, right? I have 2 factors in the denominator, so that's okay. That just means I'm going to have 2 vertical asymptotes, and that's totally fine. So we would take the first one, x minus 7, and set that factor equal to 0, and then we'd take the second one, x plus 2, and set that factor equal to 0. And then we just solve both. So for the first one, I would just add 7, and I get x equals 7. For the second one, I would want to subtract 2. Just use my inverse operations. And 0 minus 2 is negative 2. So this tells me I have 2 vertical asymptotes. I've got one at x equals 7, and I've got another one at x equals negative 2. To find my horizontal asymptote, remember I compared the degree of the numerator to the degree of the denominator. So let's look here and let's think about how this would be. I'm just going to rewrite it. This one could be a little bit tricky for 2 different reasons. The first one is the numerator. When we look for the degree of the numerator, notice I don't have any variables. There's no letters in the numerator. So a lot of people want to say, oh, okay, well then it's just 1. The degree is 1. It's actually not. If there is no letter or variable present, then the degree is actually 0. Now for the denominator, this one's also a little tricky because you might think, okay, well there's an x, and just like we found on this one, if there's no exponent, then the exponent is 1. And that's true, but don't forget that we have another x over here as well, and he also has an exponent. His exponent is also 1. So for this, we have to remember those exponent laws. If we multiply straight across, we add the exponents. So in this case, this is 1 plus 1, which is 2. So our degree of the denominator is 2. So when we compare this with our Bobo, Botan, EATSDC, notice that the bigger is on the bottom. So this is a Bobo. And remember, bigger on bottom is 0. So our horizontal asymptote is just y equals 0. So when we go to write our domain, remember our domain is all real numbers, but we just need to be careful of any holes and also the vertical asymptote. For holes, we found that there were none, so we actually don't need to worry about that. But for vertical asymptote, we had 2, right? We had 1 at x equals 7, and we had another one at x equals negative 2. So in that case, we just need to make sure we include both of those. Our formal way to write it would be negative infinity to your lowest number, negative 2 is lower. We would say negative infinity to negative 2, union, and now your lower number to the higher one, 7, union the higher number, 7, to positive infinity. The shorthand way to write it would just be that it's all real numbers, but x cannot be -2 or 7. When we go to find the range, remember it's all real numbers, but y cannot be any wholes, and y cannot include the horizontal asymptote. So again, no wholes here, so we didn't have to worry about that one, but we had a horizontal asymptote at y equals 0. I just realized I didn't have my little at there included. So for this one, the formal way to write it is going to be to say that our range would be -infinity up to, now this is the first time we've only had one number, right? For this one we had 2, for each of these we had 2 numbers to worry about. So for this one we just say it's -infinity up to 0. We close that out, union from 0 to positive infinity. So we're just saying there's just one gap here from 0. And then other than that, it's all real numbers. So the shorthand way to write it would be our range is all real numbers, but y cannot equal 0. In this next example, we've got f of x equals x squared minus 9 divided by x squared minus 2x minus 3. So remember those first steps, which are we are supposed to factor the numerator and denominator if possible. So on the last two examples, there wasn't really anything for us to factor. They already gave them to us in factor form, which was nice. In this case, both the numerator and the denominator can both be factored. So for the numerator, this is a difference of perfect squares, x squared minus 9. So when we factor this, and I'm going to go ahead and write the simplified form, we create our two binomials. One is going to be plus, one is going to be minus. Our x squared goes first, then a minus and a plus, and then the square root of 9 is 3 and 3. For the denominator, this is a quadratic trinomial, so we would want to use our x to help factor it. I'll just do that over here. So my a times my c is a -3, and my b is a -2. I know that my signs have to be a negative and a positive, since I'm multiplying and getting a negative. And then I ask myself the question, what do I multiply to get -3, but also add to get -2? So in this case, my options are going to be -3 plus 1. -3 times 1 is -3. -3 plus 1 is a -2. So I know my factors for this quadratic trinomial are x minus 3 and x plus 1. So before I move forward, I would want to ask myself, is there anything that I can cancel that occurs in both the numerator and the denominator? Hopefully you're seeing these x minus 3s. I can go ahead and cross them out and rewrite what I have left. So x plus 3 over x plus 1. This is our most simplified version. So to figure out if we have any holes in this graph, we first try to find the x value. We say, was there anything we were able to cancel? And there was this x minus 3, right? So we take that x minus 3 and we set it equal to 0. And then we just solve for x. So in this case, it's a one-step equation. We just add 3 to both sides. And I'm going to write the answer over here. We would just get x equals 0 plus 3 is 3. So I know that the x value of the whole is 3. To figure out the y value of the whole, remember that I take the simplified version, and anywhere I see an x, I just plug it in with 3. So I'm going to write a 3 plus 3 in the numerator and a 3 plus 1 in the denominator. Now 3 plus 3, that would give me 6, and 3 plus 1, that would give me 4. Now 6 over 4 definitely reduces to 3 over 2. So that tells me the y-coordinate of the whole falls at 3 over 2. Which tells me I have a whole at, and I would want to write the actual point. So the x is 3 and the y is 3 over 2. Or 1.5 if you prefer to see a decimal. To find my x-intercept, remember once I take my simplified version and any remaining factors in the numerator, so this x plus 3, I set equal to 0 and I solve. So x plus 3 equals 0, and then I just solve it. I would want to subtract 3 from both sides, and I'll bring it over here. We get x equals 0 minus 3 is a negative 3. We have an x-intercept at negative 3, comma, 0. To find the y-intercept, we take our simplified version, and anywhere we see an x, we plug in a 0, and then we just simplify. So this will be 0 plus 3 in the numerator, and 0 plus 1 in the denominator. Well, 0 plus 3 would be 3, 0 plus 1 would be just 1, and 3 over 1 is just another way of saying 3. So our y-intercept falls at 0, comma, positive 3. To find the vertical asymptote, we set the remaining factors in the denominator equal to 0, and we solve. So in this case, it's just an x plus 1 in the denominator. So we just do x plus 1 equals 0, and then we solve it. So we'd want to subtract 1 from each side, and we get x equals 0 minus 1 is a negative 1. So we have a vertical asymptote at x equals negative 1. To find our horizontal asymptote, remember this is where we're comparing the exponents. So we want to rewrite that simplified version. So we've got x plus 3 over x plus 1. My degree of my numerator, that would be, I don't see an exponent here, so that means an understood 1. So my degree is 1. And in my denominator, again, I don't see an exponent with my variable, so it's an understood 1. So this is another EATSDC. Notice my exponents are the same. And when my exponents are the same, we divide the coefficients. In this case, my coefficient is a positive 1 and a positive 1. And 1 divided by 1 is just 1. So that tells us we have a horizontal asymptote at y equals 1. To find my domain, remember it's just all real numbers, but we need to be aware of where the hole or holes are, and also the vertical asymptote. So remember, we have a hole at x equals, and what was the x value of the hole? It was 3. So we have a hole at x equals 3, and we had a vertical asymptote at x equals negative 1. So we'll write the formal way to write domain first. We would say domain is negative infinity to the lower value, in this case negative 1, union negative 1 to the higher value, 3, and then 3 all the way to positive infinity. Or we could just shorthand that it's all real numbers, but x cannot equal negative 1 or 3. For our range, it's going to be all real numbers, but we want to be aware of where are the holes and horizontal asymptote. We have a hole at the y value, remember range means y, the y value of 3 over 2, or just 1.5, same thing. And we had a horizontal asymptote at y equals 1. So when we go to write our formal way, we would say negative infinity, the range is negative infinity, to, now remember 3 over 2 is 1.5. So which one's lower, 1 or 1.5? Well, that would be 1, right? union 1, 2, 3 over 2, or 1.5, union 3 over 2 to positive infinity. The informal way would just be to say all real numbers, but y cannot equal 1 or 3 over 2. Okay, let's do this last one together. So we've got f of x equals x times x minus 2 divided by x minus 2. So the first question is, we always ask ourselves, is there anything we can factor in the numerator or denominator? So a common student error is people want to take this x and distribute it in. That x has already been brought out. If you distribute it in, you're creating more work for yourself. So we don't want to distribute. This is already factored and we want to leave it as it is. But then we want to ask ourselves, can we simplify it anymore? Is there any common factors in the numerator and denominator that we could cancel? So hopefully you're seeing this x minus 2, we can go ahead and cancel that. So we would just be left with an x, or you could say we're just left with an x over 1, right? And x over 1 is just another way of saying x. So our simplified version is just x. So to find the x value of any whole, so remember we set what we were able to cancel equal to 0, and we solve. So in this case, we were able to cancel this x minus 2. So we want to say x minus 2 equals 0, and then just solve it. In this case, we'd want to add 2 to both sides to get x equals 0 plus 2 is just a 2. So we know the x coordinate of the whole is 2. To figure out the y coordinate, remember that we just replace all the x's in the simplified version with the x coordinate. So in this case, this feels kind of weird, but we would just say, okay, well, if I just replace the x with the x coordinate and simplify, well, there's not really much to simplify. It's just 2. So that's okay. That just means our y coordinate of the whole is 2. In this case, we have a whole at 2, 2. To find our x-intercept, we set the remaining factors in the numerator equal to 0, and we solve. So in this case, it's just an x, right? And x is technically in the numerator, so we just say x equals 0, and then we would solve it. But here's the thing, isn't that already solved, right? There's nothing else to do here, it's just x equals 0. There's no dividing or adding or subtracting I need to do, so that's just my x-intercept. It's x equals 0. Now, I definitely prefer to write that as a coordinate point, so I'm going to write that as 0, 0. That's where our x-intercept falls. To find our y-intercept, remember we plug in 0 for all the x values, and then we just simplify it. So in this case, if I were to plug in 0 for the x value, I would just have 0, right? So it's just a y equals 0. And to write that as a coordinate point, it would just be 0, 0 again. So we have both an x-intercept at 0, 0 and a y-intercept at 0, 0. For our vertical asymptote, remember we set remaining factors in the denominator equal to 0, and then we solve. Now this could be a little tricky because you might look at that and think there is no denominator. How would I do that? Well, technically there is a denominator. It's 1, right? If I had to give this a denominator, I could put it over 1. So we would just say, okay, well, let's set 1 equal to 0 and then solve. But this is a weird situation. There's nothing to solve for. And 1 does not equal 0. So in this case, we would just say there is no vertical asymptote. It's just none. And that's okay. We don't have to have a vertical asymptote. To find the horizontal asymptote, remember that we compared the degree of the numerator to the degree of the denominator. So we're going to use this version because we want to have both a numerator and a denominator, right? So we'll just rewrite that x over 1. Now the degree of the numerator We don't see an exponent there, which means there's an understood 1. So our degree would be 1. In our denominator, I don't even have a variable in the denominator. It's just a constant, right? It's just 1. So that means our degree is actually 0. So this is a situation where we have bottom. So we have the bigger degree on top. So this N stands for no horizontal asymptote. So this is just none. There is no horizontal asymptote. So remember, our domain is all real numbers, but we want to be cautious of the wholes and the vertical asymptote. So we had a whole at the x value 2. And remember, we didn't have a vertical asymptote, so we just don't have to worry about that part. So when I go to write the formal way, I would say our domain is negative infinity, but we have a gap at 2. So we do 2 union 2 to positive infinity. It means negative infinity to positive infinity with a gap at 2. The informal way would just be all real numbers, but x cannot equal 2. To find the range, we want to be cautious of the wholes and also our horizontal asymptote. So we had the whole at the y value 2, and we did not have a horizontal asymptote, so we don't have to worry about that one. So for this one, I would say my range is negative infinity to that gap at 2, union 2 to positive infinity. Or we could just say all real numbers, but y cannot equal 2. Okay, here's one for you guys to try. I've given you a rational function, and if you'll find each of these components just like we did on the other pages, I will post the answers in the video description below. This has been Miss Math Tutorials.